Good morning, class. This is your instructor. Today I'm going to be talking about matrices. Matrices are basically spelled in plural form like this and in singular form like this. And it's going to be your chapter 4 from the book Finite Mathematics by Stefan Waner and Costinoble. Now, there are going to be different concepts which are associated that lead us to talk about matrices and where this originates from. So let's just consider an example of two cellular phone companies that are selling mobile phones, let's say, and one's name is Cellular and the other's name is iClone. Okay. And these both are competitors. So now it means basically that if one company wants to sell its phones, they would be more interested in their market share. One thing. There's going to be a market share. And next thing would be the customers or the customer base. And the third thing would be the competition, actually the competitors that they have, and the permanent customer base. So the CEO, let's say, of cellular company, which is company number A, has sales data. And they want to see that this is company number B. It has its own sales data, and this CEO comes to know that this company's policies somehow have attracted the customers to the point where they have acquired a loyal base of customers so that they don't move. Once they have that base does not shift, or the customers don't change brands, and they're so fiercely loyal to this company. In this way, this company would be feeling threatened or lose its market share to iClone. Therefore, the CEO of this company requested his officers to make a projection or a projected report of its market share, let's say in 2, 5, and 10 years' time. Okay? 2, 5, and 10 years' time, where this company is going to be, let's say in 2 years, or 5 years and 10 years in terms of its market share, and especially when they would want to know how many customers would switch to other mobile service providers or the cellular phone companies that are selling phones. And they are particularly concerned about iClone because this company has its loyal brand of customers which are steadily growing. Okay, so now they would want to know, first of all, what is the sales value, and in 5 years the projected sales figure is going to be somewhat different, and then 10 years time. And they're also concerned about whether they're going to be losing out in the long run. So they would want to know about the performance and the sales. So they would want to compare the sales of this company with this company. So in this way, matrices are aligned, and the concept, you can just place the matrix in this way. You can just have a box type thing. Okay, I'm just going to be rubbing this part. Just going to be having a box type thing here, where you can just say that various years could report. For the first 5 years, this year number 1 could have 1 million sales, 1 million customers, and then this is for particular as many rows you can have. So rows could be year number 1. This is 1990, let's say. Okay, this is 1991, 1992. So for 2 years, I say. This is various quarters, could have 1, 2, 3, and 4. So these are the quarters, and then you can have 1 million. And in this 1.5, then you can just simply have 1.6, and then you can just simply have a decline of again 1.2, And the year number 2, perhaps 0.8, 0.79, and 0.9, and things so on. So forth. You can just simply have maybe 0.95, and then you can have 1.5. Perhaps they would be improving their policy, or maybe other companies have left, or they are thinking of some better policies to attract the customers. In this case, we have 2, and then 2.5 and 3, so onwards. You can have rows, and you have versus columns. Now, this is actually R into C, which is easier to remember if you just write it like RC. And that is row into columns. So you have M rows into N columns, MN, okay, or RC. And these are different numbers, or you should know that M would always represent the first, N would represent the second, where rows come the first, at first, and C is at the second place. So this could be a rectangular array. As you can see, it's a rectangular array where you have 3 rows in this case into 4 columns. Okay, so this is a 3 into 4, 3 by 4 matrix. Okay. Then now a question can actually come to you as to, can this be a square matrix? Can it be an equal matrix? The answer is yes, it can be a square matrix. Can be 3 into 3, can be 3 into 4, can be 3 into 5. But if you have 3 into 3, it cannot be aligned with 3 into 5 or 3 into 4. You can't add this over this. So there are a couple of concepts that we'll be considering. First is the properties. Then is addition. Then we have subtraction. And we have scalar multiplication. Now, scalar is a quantity that is represented in the form of a number. So when you have scalar multiplication, or you can also have multiplication with each other, provided that they have equal dimensions. And dimensions, I mean rows and columns should be equal. So rows of first matrix, and this can be matrix A in this, and in our particular example, other parties' data would be in matrix B. And they're easier to handle this way. Now, why do we say that we're multiplying or dividing or adding in this way? Because this is the most efficient way of multiplication and division as per the rules that we will be studying now. And then we also have transpose and identity matrix and inverse of a matrix. So, but if I have time, just look at these few basic concepts, few basic questions, which are very essential for you to understand and reiterate. I will just reiterate this. The first thing is the properties that I'm going to be talking about, which is the commutative property. We have associative. We have the identity property of addition and the property of having the inverse. Okay. So basically, it's not inverse in the sense that you have been studying about, it's completely the opposite way. So it's first, if it is A, the complement, I would just say it's going to be A minus or minus A, where you have minus multiplied with this entire matrix. So now, when we talk about properties, they are the same for both. Where we have associated properties, that was A plus B into C is, or C into A plus B, I don't think that should be a problem. Then we have distributive property, okay. This is sort of like, commutative, we have associative, then we have commutative properties, and then this is sort of like a commutative property, but we also have associative where we have A plus B plus C with 3. Okay. A plus B plus C, and I can have the bracket removed from here till here, and then we can have plus C. So this is like commutative, very similar. So either you multiply it like this, or this change in its position won't have much of an effect. And we also have associative, where this can be A plus B plus C, but the bracket shifts. Okay? Then we have other identity properties as well. If I say that A is a matrix, what I would additive property would be just the same for addition. But for if I say you are subtracting something, that would just inverse for an inverse. You just subtract and that will give you a 0 in this case. So that means that if it is A minus A, it's actually 0. So from subtraction, we actually got the additive property. Then also we have the multiplicative one, which says that A into a 1 would give you actually A, right? So this is identity, because it would not change its identity. So in this way, if you multiply it with 1, just gives it its own value multiplied by itself. Multiplied by a number which does not change the identity, or it would just give itself the final outcome. Okay. Now we have similarly we have distributive properties, and then for just for multiplication we have A plus B is equal to B plus A. This is the simplest of the commutative properties. Okay, so in other words, these are the same that we have already done for real numbers, and this means that these are real numbers with both positive and negative values. Just like in the real number line, we have negative and positive values, so we have negative and positive integers here. So this is going to be as if in a real number line we have a rectangular array. Array is like something you just distribute along the line. So, but in a rectangular fashion, you just arrange the numbers. Now each number would have an ith column, the row, and jth column. Take it? So that means we have ijth position of a particular number here. And if I say that this matrix is A, so for A into ij, it would mean that I am actually giving the location for a particular number. Now how am I supposed to express it in the form of a number? This would be, I can also represent it as a small a with, now how many rows, actually if I want to have, let's suppose this number expressed in expressed or to be expressed for writing in this array, I would have, this is the third row and this is third and second column, so I'm just going to be writing this 2. So you're not just going to read, pronouncing or saying it as 32, which is 3 into 2 matrix, where this has ij position, and this would just precisely give you the location of that particular entry. So each number is known as entry. Okay. Then we are going to be doing detail the properties, whether it's distributive, commutative, or we have associative properties here. And this was just for multiplication, but we have other properties where we have, multiplying and dividing for a larger base of numbers. And then, okay, so for addition, the rule stands that both have to have the same dimensions. For subtraction, the rule holds that both have to be of the same dimension. And scalar multiplication is when you're multiplying. So I would say that if it is like 2, 4, 6, now you can multiply with different dimensions so that for every row would be multiplied with every entry of this particular column. So for multiplication, you need to have at least this value will be multiplied with this with this, and then you can just simply this with this, and this with another one, because if it is not of the matching dimensions, then you cannot multiply them, because then this would be, this has to be multiplied with something, otherwise the answer would be returned as nil or null to you. Let's just go towards the book, and okay, the final concept is transpose. So transpose is just to convert the horizontal array to vertical. So I would say that this has to be transposed as 2, 4, 6, 7. So if this matrix is to be transposed, I would say that this is 1, 1.5, 1.6, and 1.2. Okay, and then 8, 0.7, 9.9, and 0.95, and 1.5, 2, 2.5, and 3. So you get a transpose of the matrix, and it's just when you are transposing something, so you can just simply represent it as a T. So when you take a transpose of this transpose, it would just return A to you in this case, right? So let's just go towards the book and see what we learn. Then we can just simply follow with the questions. Oh yeah, one property that I forgot to tell you was that the distributive one. So let's suppose if I have something like this, and I multiply 1d with this. So this would result in a dA plus d into b plus d into c. Okay, so this is basically the distributive property of matrices. Would hold true for this as well. So now we just okay, now I hope you can see the book. Now I'm just going to be going, sliding down and explaining. So now you have m into n matrix, and okay, you can just simply see the font clearly. Yeah. Now I've already given to you how we're supposed to be narrating the dimensions. So we have a which is equal to a particular value of rows. So you can just simply see that there are 2 rows and 3 columns, 2 into 3 matrix. And in this way, we have a B, which is with 4 rows, 2, 10, minus 1, 8 is the first line, first column of the, with 4 rows, bearing 4 rows. So we have 4 rows into 2 columns. So first column and then 3, 44, 3, 3, this is the second column. And the entries would be 2, 0 for the first, and then starting from 2, 3, 10, these are all individual entries. And you can just go through with this. We have values, like I told you, if you want to display the values in the form of variable, which can, it's a constant but with varying values of I and j. So this would give you the precise location, or where you have to indicate the location from the question which is given to you, problem that is posed to you. Then you can just simply locate that value with the given numbers of the dimension where the location is actually. So we have A21 as 33, as you can see, it's the second row and first column. Then you can just simply have a number of entries, and they say that 2 matrices have to be, like I said, equal. And they say that 3 into 4 can never be equal to 3 into 5 matrix. Similarly, they have given you an example here, as you can see that A, okay, so now A is equal to B in this case, right? So now you see, this is a variable, so you don't have to get too scared of this. it just simply says that since both have to be equal in dimensions, or if it is an equal matrix, okay, so now for equality, it will be very easy for you to find out the value of this variable. So if you have 7, 9, 0, and -1 both have the same values, but you don't have the value for x. Now x has to be equal to 0 in this case, and then y plus 1 is equal to 11. So you can find out the value of x, which is 0, and y plus 1 is equal to 11 would mean that actually y is 10, right? Now if I want to place the location, I can just simply write here that y is 10 plus 1 is 11, and then it's 0. And A1, 3 in this case would be equal to B1, 3. So this is the second matrix, and since A, so this is the third column, and it's the first row, so this is 1 into 3, so it's 1, 3. And this is B into first row and third column. Just keep going with this. As you can see, similar procedure is repeated here. X equal to 0, y plus 1 is 11. So y is 10 and x is 0 again. Right. So now they say that since they are all equations, these are all equations. So 7 is equal to 7 is one equation, 9 is equal to 9 is one equation. And x equal to 0 is the third equation, and then we have 0 is equal to 0 and -1 is equal to -1. But the most interesting for us is the ones which have variables that mean they're unknowns. So we just put interested in unknowns. For multiplication now, this concept will be used further, but we have a concept of square matrix, we have a rectangular matrix, we already done rectangular. If you need square, you just simply cut this variable part off and you just have the square matrix form. So single row would mean a row matrix, and if a single column is going to be a column matrix or a column vector in this case. And then if we have just equal rows and columns, we have a square matrix in this case. So now this is, it could be a 2 into 2, 4 into 4, 3 into 3 matrix, it would be a square one. So this is a square matrix in the third. So the sixth entry in this case is the square matrix. Now we have 1 into 5 is the row matrix, and this is the column matrix. So now addition and subtraction, like I have told you, if you're just adding these values up, so whether you add individually or you can just simply add them up and then find out the value of the location. The location part, I would say rather, the location of the value of those two matrices that have been added, okay? So if A has particular value, what this is trying to tell you is actually this is one entry, let's say this entry, okay? And this is other entry, which is this one. In this case, second matrix, okay? So now either you just simply add them up individually as Aij plus Bij, or you can just simply add them up first, and then you simply write it the final equation as the value it will be having. It is just the same thing. So let's just say if they have just mentioned that Aij in this case is first row and first column plus first row and first column of the second matrix. So you just add them and you get first row, first column, final value of 3. Or you just simply add them up, or you can just simply write in the final as 3ij, which is 3 first row and first column. Or you simply just individually write as 2 first row, first column plus 1 first row, first column, and you get equal to this ij. So this, just take out this first row, first column common, and you have 2 plus 1 into 1. This is 1 plus 1. So this is 2 plus 1 and bracket off. So it's 1. You can just simply open it with the bracket off, or just 2 plus 1 with bracket closed and 1 into 1. Okay, so you can have this as common taken out. Then we have some other quick examples of how to add. So when you're adding something for matrix, you need to add the corresponding values. For multiplication, the rules are slightly different. But for addition and subtraction, so if you have first entry, you add it with the subsequent corresponding entry of the second matrix. So 2 plus 9 would be 11, or minus 3 plus minus 5 would be minus 8. 1 plus 0 is 1. 0 plus 13 is 13, and minus 1 plus minus 1 would be minus 2, and 3 plus 3 is 6. when you subtract 2 minus 9. Okay, so you can't just subtract the other way around because it's just first minus the second. So it's 2 minus 9. Now it also depends upon you which one you want to keep first and what your target is and what you want to find out. But in this position, so if we have 2 minus 9, you get minus 7. Minus 3 and plus 5 in this case, because minus is plus, so minus 3 plus 5 would give you 2. And then we have 1 minus 0 would be again 1 and 0. Minus 13 is minus 13, 1 minus 1 and plus 1 would be 0, and 3 minus 3 is 0. So both of them are 0. Okay, now I gave you an example way before, so this is another example where you have auto parts store chains has 2 outlets, one in Vancouver and one in Quebec. So among other things, it sells wiper blades, windshield cleaning fluid, and floor mats, and they have sale figures reported for January and February. So if you just want to find out, like they say that they have the sales variables, you can for wiper blades, they have variable sales for different cities. In this case, it's 20 and 15. So you have for February variable sales for a particular product that they're selling, which is wiper blades in this case. Now, what do you want to find out? In this case, perhaps you would be trying to compare the sales of both these months and see whether there's a change in that. As you can see, they've asked you to use the arithmetic to calculate the change in sales. So if you have 2 and you want to find out the change, so you will naturally be subtracting. So if you have just constitute by converting it into matrix, so just make a rectangular bar. This is the bracket. So we have 20, 10, 8, and 15, 12, and 4. And this is the second matrix F. It's just like this very conveniently write A and B as well. But this is J for January and F for February. So we have 23, 8, and 4, and 12, 12, and 5. So we have now 23 minus, okay, so now this is going to be subtracted, this J will be subtracted by this, so minus 23, okay, so now as you can see, or you can face, if I told you that there are, simply if you're just supposed to be subtracting just to find out how you subtract, you're just going to subtract 20 and 23. But if you want to find out the change in sales, and this is what your objective is, then for change, second minus the first is equally valid. You can just find it out any way you want. So if you want to find out the difference of the two, so the second value comes first minus the original. So the change would be then the second minus original, and if you want to find out the percentage, then you just divide it by the original value again. So we have 23 minus 20, okay, and this is like this, 23 and minus 20 gets you 3. Then we have 12 minus 15, so gives you minus 3. And then 8 minus 10, it's very simple, just corresponding values are subtracted, you get 0, 4 minus 8, minus 4, 5 minus 4, it's 1. And then you just report it in the form of a matrix. And we have scalar multiplication now. Scalar is just a number, and you will just multiply it by some number, then you multiply each and every element of that. So for instance, they're giving you a matrix with these entries, 5 by 2, minus 3, 1, 0, minus 1, 5 by 6. And you multiply each entry by number, a scalar quantity, which is 6. And so now 6 into 5 by 2 is actually 15, because 5 by 2 into 6 is 2 gets cancelled, 2 into 3 is 6, so this is 3, so 5 into 3 is 15. Similarly, 3 into 6 is minus 18, so 6 into 1 is 6. And this is 0, and this is minus 6 and 5, because 6 and 6 gets cancelled. Again, they have given you another example where they have, in terms of dollars now, given you value in Canadian dollars for 2 cities, Vancouver and Quebec, and they've given you the sales value. And they want you to report this value in US dollars. So you know that US dollar is stronger than Canadian dollar. So that if I were to express in terms of Canadian dollar, how would I express? So just simply use the calculator to find out as well. You can just simply use calculator. And there's 1. So if let's just say that 1 Canadian dollar is actually equal to 0.65 of US dollars. So how many, just for general knowledge sake, US dollars would be expressed in terms of Canadian dollars. So that would be 1 by 0.65. So that means for 1 US dollar, we would get actually 1.53 Canadian dollars. Okay? So now this is just for general perception. And now, since this is already in Canadian dollars and we want to multiply it by some value which would be converting this into US dollars, and since this dollar is stronger, so this would reduce this number. So we have the dollar as 0.65. So, like I said, that if $1 is equal to 1.53 Canadian dollars, that means that 1 Canadian dollar is 0.65 US dollars. So that is 65 cents actually. So just multiply it with 65 cents. So 0.65, and this will give you a reduced value of this. Okay? So this reduced value is actually 91. So you simply multiply 140 with 0.65. And you get 91. Okay, so similarly you get all the other values, just multiply each and every value with all the entries. So this value will be multiplied with this is all. It's simple when you just have to multiply one quantity, this is scalar quantity. But when you multiply various other values, then you need to also be considering or considerate of how many rows are to be with the particular entries in the column. So rows would be with column. And now you have A and B. So C, okay, so this is just an example where you have been given some individual value of 4A, X, B, and A plus 3C. So you multiply 4, and you get 4 into 2 is 8, minus 4, 0, and 12, 4 into 3 is 12, 20, and minus 12. Similarly, we have X and B. So this is very simple to just track because we have a variable that cannot be gelled with the numerical values. So X, 3X, minus X, 5X, minus 6, X, and 0, and we multiply 0, 0. And the third one is X, Y, W, Z, T plus 1 and 3. So now they've actually asked you to find out A plus 3C. So first of all, we're going to be multiplying it with 3. 3X, 3Y, 3W, 3Z, 3T plus 3, and 9. Okay, so it's 3D plus 3 and 9, all these values. And then you multiply with, you add it with 8. So now, very simple, just 2 plus 3x minus 1 plus 3y and 0 plus 3w. So it's just 3w. And then we have 3 plus 3z, 5 into 3t is 15t plus 15. Oh, sorry, this is addition. So it's 3t plus 8. Okay, so now you can't really add it. There have been no 3, so this would just be 3t plus 5 because you can't really multiply with t variable. Had it been a multiplication question, then you would have simply multiplied this. So now you just, if there was no 3, then you just simply write 3 plus 8, just add it, but you can't gel it with the variable. And then we have minus 3 plus 9, so it's, again, this is 9 minus 3 is 6, we have 6. Okay, so now we have the matrix where you can have a negative value, which is the exact opposite, the complement, like I said, minus A. And just inverse or change all the signs in the first entry. So it's minus 4, 2, 0, minus 6, minus 10, and 6. 0 matrix where all entries are 0. Okay, so these are properties. Now you have distributive law as opening the brackets and solving it. And you have a commutative A plus B. So you can also have multiplication with A plus B into C. So you can have C with C into A plus B. Whether you write it here or here, it's just the same. Okay. So A plus B into C or A plus B C here, like I already told you. So this is they're just given the additional one, but it would equally hold for the multiplication values. So for A plus b plus c is actually a plus b, so we have not done this, so I can just simply go back and see. And this doesn't change, so anything with 5 0 is again this equal to 0. Transposition, okay, this is interesting. When you revert, so m into n into, and then it's n into m, okay? So this n would actually be cancelled, so it's m into m. In other words, the rows should be with the number of columns, and that should be equal. So then we can transpose. So we have 215 minus 301. 215 and minus 301, so you just transpose with equal dimensions of columns or rows. So if you are transposing the column, should have equal dimensions, equal entries in this way for rows, and the entry numbers should not change because otherwise you can't really convert all the values in this case. This is second column, you have equal entries that particular dimension. If you transpose now 2010 33 minus 22, sorry, this is minus 22, so it's going to be 33 minus 22, 0 and 5. And then we have 1, minus 1, 2, minus 2. So this is now 3 into 4, because this is 3 rows and 4 columns. And this is 4 rows now into 3 columns. So in this way, we can just simply have what is the same thing is that we have to multiply and make sure that the values of the rows should similarly be equal to the values of the columns. So in this case, there are 4 columns, and here you have converted to 4 rows. Whatever you're converting should have the same entry values in terms of number of values, not the numerical number associated with it, but the place, the ij place, should be actually of the corresponding nature. So now just simply transpose this, and then again transpose it would give you the same matrix. Okay, like I said, this is the last property we have. This is very again similar to the commutative property. Like I said, this can be just taken out. And you can also see that when you transpose the whole value, or you just individually transpose and then add, it would give you the same value. So if you have the same value of this is transposed, so let's say this is transposed, and then you just add them together. So you need to have the same, so 2 plus minus 3, so all these values will be individually added, and then you can just simply, or this 2 minus 3, so you can just have one value, and then you can just have 1 plus 0, so it's 2 minus 3 is minus 1, and this is 1, and this is 4. So then you can just simply transpose this, or you can just simply individually transpose them and then subtract. So just to give you minus 1, 1, and 4. Okay, so just again the same thing. And now we come to the exercise. And you just simply look at these questions. I'm going to be doing a few of them so that you can understand how to attempt. If you have any confusion in those questions, you can always ask. And now I'll be writing down the values of the questions. Okay. Okay, so we have the first question as 1501 by 4. So A is 1, 5, 0, and 1 by 4. And they have given you this location. It's very similar to having an address given to you and then you just reach that because of the name. It's just like a street number that you would have. And then you can just simply go there. So now A is a representative of this, and it's just the entry at I, which is 1, is the first row, and J, which is the third column. So this would be this one. Okay? Similarly, we have 4455 as B12. This is question 2. 4455. and we have B12. Now we have the first row, because this is one row, and second column. So this would be this column, okay? Then we have a big array of matrices where you have E given to you as, this is E11, E12, and this is just E1Q. Okay, there's E13, and then E1Q. Then we have similarly E2, second row, first column, this is second row, second, E23 up to E2Q, and then we have EP1. So I'm just going to make 3 dots, EP1, EP2, EP3, EPQ. So now you know that the dimensions are P into Q, where we have P rows and Q columns. It's very easy to remember because, like I said, RC is just a symbol that you can use just, or MN. So it's for row and this is for column, so you can just simply see that first come the rows and then come the columns. And if you want to find out some E22 in this case, we have just given you E22, so we can have in here, because this is the second column and second row. Okay? So now this is coinciding with this one. And similarly, I think you can just do the rest. Now we have so okay, this is 11th question. I would like to solve this for you. There are other questions with similar connotation, similar method of doing it, and just looking at any other important question in the middle somewhere. Okay, so I think they're all basically the same, except for 11 is a bit different. It just makes use of the concept of addition. So we have x plus y, and y plus z. Then we have z plus w and w. We have z plus w and w, and then we have is equal to 3, 5, 7, 4. 3, 5, 7, 4. So guys, like I explained way just in the middle of the lecture, I think that these are basically equations. So for equations, x plus y is equal to 3 is the first equation. Then, okay, so if you look at this second equation, this is y plus z is equal to 5. Third equation is z plus w is equal to 7, and the fourth one says that w is equal to 4. So now, if you want to place this value in here, so you can find out the value of z in this case. So since w is 4, so 7 minus, so z would be, actually, or let me just say that z would be 7 minus 4, and that would be 3. Similarly, when you have the value of z, then you can find out the value of y. Y would be putting the value of z in second equation. So this is y is equal to 5 minus 3, which is 2. And for x is equal to 3 minus 2, which is actually 1. There goes the question. Similarly, you can see other questions with similar details with subtraction. You just follow the same rule, and let me see if there's another question. So we have like this is question number 18, 2a plus 0.5c. So it's 2a plus 0.5c. Okay, so I have to see which example this is. This is question number 18, and they've asked us to. Okay, so they have given us the values. Let me see if I find the values on matrix. Okay, yeah, so they have, if you go up, they say that in exercise 30 to 20, and this is question 18, evaluate the given expression. So they've given us the values of matrix. For A, we have A 0, 1, and -1. And we have -1, 0, 2. -1, 0, 2. So first of all, we want to find out 2a is actually 2 into 0, -1, 1, 0, -1, and 2. And that would be, I'll rub this off. Okay. So this way is going to be 2, this is 2 into 0 actually. So it would be 0, -2, 2 into 1 is 2, and -2, this is 0, and 4 for this. This is 2a. So we have 2a equal to this. Now 0.5 into c. And then you add them. So now what is c? Okay, so now 0.5 of c. I'm going to be directly adding because there's a shortage of space, 0.5 of c. So now plus 0.5 of c, which is, now what is c? 0.5 of c. And c is 1 minus 1, 1 minus 1, 1, 1, minus 1, minus 1. Minus 1, okay? So you can just simply look at this that this is actually plus of instead. So this is 0.5 c is equal to this. Is equal to 0.5 of this. And plus, so I'm going to be writing as 0.5. Okay. 0.5 into 1 is 0.5, and this is minus 0.5, and this is 0.5, this is 0.5, minus 0.5, and minus 0.5. Comes the value of c, right? Now, they've asked us in question 18 to find out 2a plus 0.5c. So I have to add 2a and plus 0.5c. So this, I'm going to be rubbing this off. Or should I write it over here? So this would give us, so 2a was actually 2 into 0. So this is 0 plus 0.5. So then that would be 0.5. Okay. Then for minus 2, and this is minus 0.5. So this is going to be minus 2.5. Then we have 2 plus 0.5 is 2.5. Minus 2 minus 0.5 is minus 2.5 because this is addition, okay? Had it been subtraction, then this would have actually been plus. So plus 0.5 minus 2 is actually a minus 1.5. So then you have to be very careful about values. Then we have, okay, so this is this 0 plus 0.5 is 0.5 minus 2 plus minus 0.5 is minus 2.5, then 2 plus 0.5 is 2.5, and 0 plus 0.5 is 0.5. And minus 2 minus 0.5 is minus 2.5, and 4 minus 0.5 would be minus 3.5. Okay, so here goes the addition and multiplication with this. So guys, I just hope that you can do this. So similarly, we have 2AT. This transpose, we have A transpose as this question 19. Okay, so with the same data for matrix A, if you transpose this now, it would actually be, so AT in this case would be 0, 1, and minus 1, and this would be minus 1. So okay, let's just look at the dimensions, which is 3 rows and we have 2 columns. Now we have, in this case, 2 rows into 3 columns. So as you can see, when you transpose, the values have to be the same, opposite vectors. Then we have minus 1, 0, and 2. Okay, so now we have A transpose, and they just asked you to multiply this. So 2AT in this case would be just 2 into 2 is 2 into 0, 0, 2, minus 2, minus 2, 0, and 4. So now here you go with this 19th question, and they're very simple questions. You can just simply multiply with the basics, and then you can also look at some bigger questions with similar values of a matrix in the matrix format that we have already done, the similar format examples of the applications. So guys, I just hope that you have understood the concept. So I'll be just seeing you next time. So thank you very much.